Today is a great day. In a couple hours, you and your friends will have finally arrived at Funland Theme Park, a trip you've been looking forward to all summer. There are so many rides to ride and so little time to do it in, so naturally, you and your friends pull out the park map and begin planning a route that will hit every attraction in the least amount of time. You all agree that while there are certain rides that you all definitely want to go on multiple times, such as the Drop of Doom and the Flying Phoenix, everyone wants to see every ride at least once before repeating another ride. You guys also agree that whatever path of rides you guys decide to take, it should start and end at the same location, such that it completes a loop. With the following rules agreed upon, your friends start scribbling and tracing out paths on their own maps, trying to find the best route that takes the shortest distance, and you look down at your own map and begin thinking about how to best plan out the trip. For simplicity's sake, and for my sanity's sake, I'll be marking the location of the rides as dots for the rest of the video. So go ahead, give it a try. Pause the video, copy down the map on a sheet of paper, and try and see if you can draw out a path that hits every single ride without repeats, and also starts and ends at the exact same location. Give this fancy connect the dots game a try. The best way to fully appreciate this puzzle is to play with it for a minute. This puzzle is actually one of the most famous problems in the field of optimization within mathematics and computer science, and goes by the name of the Traveling Salesman Problem. It was coined this name because the original inspiration for the problem was a poor salesman who had to visit a set of cities to do business, and being on a tight budget, the salesman had to try and figure out the shortest path that went through every city exactly once. When mathematicians and computer scientists discovered this little puzzle, they decided to generalize it to dots and lines, because once you solve the most general case, you solve the problem for a whole slew of people, whether it be restless riders or prudent peddlers. But let's get back to your solution for a Funland theme park problem. You might have realized that what seemed like a simple puzzle on the surface actually is a little bit more complicated and tricky. Did you get this path? Or maybe this one? Well, the actual shortest optimal path turns out to be this one. So did you get the correct answer? If so, give yourself a pat on the back. It's not an immediately obvious answer. The question is though, how did you come up with that solution? You might have just taken a look at the dots on the screen and just used some sort of intuition, some sort of sense to trace out a circuit that hit all the points. I mean, that's what I did at first. It just feels like for a shortest path that starts where it ends, you should kind of travel in a circularish direction, and maybe you just went with your gut on how the dots should connect. We didn't use any formula or precise strategy to come up with that. It was just pure intuition. Okay, but our intuitions can only take us so far. It might be easier to solve a problem with fewer spots intuitively, but what if instead I gave you this puzzle? All of a sudden, it looks a lot harder to decide where to start and how to continue. In order to tackle problems that have more dots, we need to be a bit more strategic in our planning for connections. We can start by maybe setting some sort of a rule that we follow so we're consistent with how we plan our paths. For instance, let's say we always start at a point closest to the top left corner, and say that we look at all the points that don't have a connection yet. And then out of all those points, we look for a point that is closest to our current one, and then draw a path to it. Then we repeat this process for the next point, look at all the points without a connection yet, look for the closest point, and then draw a path to it, and then repeat it for the next point, and the next, and so on until all the points are connected. And then of course we draw one final path from the last point back to where we started, and voila, we've generated our path. This is great. Now that we have this rule to follow, it doesn't matter what kind of puzzle we're given, whether it has 3, 20, or even 50 dots, we can just follow the rule we've created and generate a path without having to rely on pure intuition to solve it. This rule-making strategy to making solving hard problems easier happened so many times in math and science that they gave it a fancy word: heuristic. This heuristic or rule of thumb we just went through to approach our puzzle actually has a specific name. Since we're finding the closest neighboring dot each time, it's known in the business as the nearest neighbor heuristic. Okay, so heuristic's good, problem solved, video over, right? Not exactly. See, we just provided a way of coming up with a circuit that hits all the dots and seems pretty good, but no one ever said that it would be the best. Remember, we don't want to visit every ride in the amusement park in kind of a quick time. We want to visit every ride in Funland theme park in the shortest time possible. And, spoiler alert, the nearest neighbor heuristic doesn't actually guarantee the shortest route every time. In fact, let's take our old example with 20 dots. This was the path generated by the nearest neighbor heuristic that we were so happy with, but it turns out this is actually the shortest path. So, heuristics in general are great rules of thumb for solving problems, but unfortunately they don't always guarantee the absolute best answer. They're more like approximations. Wait a minute, you might be thinking. If these heuristics you told us about don't actually guarantee the shortest path solution, how did you get the optimal solution before? Well, there is one way, but it's not pretty. In theory, you could just check every single possible path and then compare their lengths and choose the shortest one. Alright, seems simple enough, you might ask. How many circuits do we have to check anyways? And the answer to that question is exactly where we run into the ugliness. For example, let's take a look at a friendly example with only 5 spots. How many loops are there that hit every point exactly once and start where they end? Well, we have 5 options to choose for where to start. From there, we have 4 different options for the next spot. Then 3 remaining options for the next dot, then 2, and finally only 1 option for the last unconnected dot. And then of course we have to connect it back to where we started. So that gives us a total of 5 factorial or 120 different paths to choose from. In fact, when you're given n number of points, the total number of cycles that you have to check through will always be n factorial. Let's go back to 5 points. Having to check 5 factorial or 120 different cases is already looking pretty daunting. But I guess you could do it with a couple sheets of paper and a whole lot of willpower. But even the strongest of wills will soon realize that this number n factorial blows up quite quickly and very soon reaches an impractical amount. For example, what if we just increase the number of dots to 20? All of a sudden, the number of unique cycles would be 20 factorial or 2.4 quintillion. And forget about trying to check every unique path for a puzzle of 50 different dots, because you'd have to crunch through that number of cycles. To put in perspective just how large of a number and how long it would take to process, if you took the world's fastest supercomputer, which at the time of making this video can compute approximately 1 quintillion cycles every second, and let it try to brute force its way through, it would still take about that many billions of years to compute. Given that scientists predict that our sun will explode in just 7 to 8 billion years, it seems like a losing battle to try to solve this problem through brute force. There has to be a better way. And there is. The Traveling Salesman Problem had been known since the 1920s, but it wasn't until 1962 when the company Procter & Gamble offered a $10,000 grand prize for whoever could solve the shortest path for 33 cities that the puzzle went viral in America. And within the same year, 3 incredibly bright minds, Richard Belmond, Richard Karp, and Michael Held, managed to crack the code. Held and Karp were working together in New York, while Belmond was working by himself in California. And both groups managed to independently solve the problem and publish their solutions in 1962. Now, known as the Belmond-Held-Karp algorithm, or sometimes just the Held-Karp algorithm, it is one of the most foundational pieces to a whole new field of problem solving called dynamic programming. I won't go through the exact details of the dynamic programming method in this video, but it is a fascinating algorithm and I highly recommend you check it out. What I will tell you, however, is that this algorithm managed to reduce the number of calculations needed from n factorial when we had to use brute force earlier to just 2 to the n times n squared. What does this mean? Well, Remember that example with 50 dots and the supercomputer that compute 1 quintillion cycles per second and would take many, many, many heat deaths of the sun to complete? Well, if we use the dynamic programming method with 50 points, the number of calculations would be 2 to the 50 times 50 squared, or about 2.8 quintillion cycles. With the supercomputer, that would boil down to just 2.81 seconds. And again, dynamic programming, unlike the nearest neighbor heuristic we mentioned earlier, always provides the shortest path, every single time. But, and there's always a but, the more astute observer might notice that 2 to the n times n squared is still exponential, and thus really, really fast growing. Compared to our friendly straight lines and polynomial equations, 2 to the n times n squared explodes monstrously fast. While dynamic programming might be able to handle 50 dots, if you just gave it 100 more for 150 total dots, suddenly we're back to many, many, many billions of years. Back to multiple heat deaths of the sun timescale again. Okay, we've gone over a few methods of finding the shortest route through a collection of points. The nearest neighbor's heuristic is quick and simple, but doesn't actually guarantee the shortest route. The Bellman-Held carp is the fastest algorithm that guarantees finding the shortest route, but it becomes slow and unusable as the number of points gets higher and higher. What we want is the golden heuristic, one that is fast and also provides a solution as close to the optimal solution as possible. Let me introduce you to the Christofides algorithm. Developed by Nikos Christofide in 1976, Christofides algorithm is the perfect heuristic that meets both of our criterias. Christofides is considerably faster than the Bellman-Held carp algorithm. While Bellman-Held carp takes 2 to the n times n squared calculations, where n is the number of points, Christofides only requires n cubed calculations. And this is an insane improvement. Remember when we mentioned that the Bellman-Held carp requires that many billions of years for 150 points? Well, with the Christofides algorithm, it would only need about 3.3 times 10 to the negative 13 seconds. However, Christofides is still a heuristic and doesn't guarantee an optimal solution, but it is the best approximation algorithm that currently exists, and it guarantees that its solution will always be within 150% of the cost of the optimal solution. But before we get to the algorithm, there are a few basic concepts that we have to introduce first. The first concept is minimum spanning trees. A spanning tree of a graph represents an assortment of edges such that all the points are connected. Now, a minimum spanning tree is just a spanning tree that has the least total edge weight out of all the possible spanning trees. To see what I'm talking about, the following are all examples of spanning trees of the graph, and their total edge weight is shown in the top right. However, this last one is the minimum spanning tree because it leads to the least total edge weight. Let's get familiar with some notation before moving forward. We are going to use the letter M to represent the collection of edges in the minimum spanning tree. C of M will represent the cost of M. This is the sum of distances or costs of the edges in M. You can see that this value is 21.4. G will represent the nodes in our graph. And T of G will represent the edges in the optimal tor of this graph G. What we're going to prove is that the sum of all the edge distances in M is less than or equal to the sum of all the edge weights in the optimal tor T of G. Let's say we remove one edge from the optimal tor. All these edges are representing distances between 2 points. So it's pretty straightforward to see that no matter what edge we remove, the cost of the optimal tor of the graph minus an edge will always be less than the cost of the optimal tor of the graph with all the edges. Let's analyze the graph when an edge is removed from the optimal tour. And notice, all the points are still connected. This is exactly the definition of a spanning tree. So, if we remove any edge from the optimal tour of the graph, we end up with a spanning tree. Now remember, we had M represent the minimum spanning tree. Again, this means the sum of the edge distances of M will be less than or equal to the sum of the edge distances of any other spanning tree of this graph. And because the optimal tour minus an edge is a spanning tree, we know that the cost of M has to be less than or equal to the cost of T of G minus an edge. And because the cost of a minimum spanning tree is less than or equal to the cost of the optimal tour minus an edge, we know that the cost of the minimum spanning tree has to be less than or equal to the cost of the optimal tour of the graph itself. This is the first important nugget of knowledge that we need. So let's move it to the bottom so we can refer to it later. Okay, the next building block concept that we need for this algorithm is minimum cost perfect matching. So given an even number of vertices, a perfect matching is a way to pair up all the points. We're interested in the lowest cost perfect matching. So we're interested in the perfect matching of the points that lead to the lowest sum of the edge distances. There are many perfect matchings for the graph, but this last one here has the smallest sum of edge distances. Okay, we got to go over some notation again. Let P represent the edges in the lowest cost perfect matching, and let S represent the collection of vertices in this specific graph. Now we have T of S represent the optimal tour of this graph S, and you can see the tour to the left. What we're going to do is color every other edge of the optimal tour blue and the remaining edges green. So P of B are the blue edges, while P of G are the green edges. What we're trying to show here is the sum of distances of the edges in P, the minimum cost perfect matching, is less than 1/2 times the sum of the edge distances in the optimal tour of the graph. Okay, how do we get there? Well, we colored every other edge in the optimal tour blue, and what can we tell about this assortment of edges? Well, they're a perfect matching. Because P is the minimum cost perfect matching, we know that the sum of the edge distances in P will have to be less than or equal to the sum of the edge distances of the blue edges. The other half of the edges are shown in green. And what can we tell about these edges? Again, the green edges themselves make a perfect matching of the graph too. So once again, because P is the minimum cost perfect matching, we know that the sum of the edge distances in P will be less than or equal to the sum of the edge distances of the green edges. Because the cost of P is less than or equal to the cost of the blue edges, and the cost of P is less than or equal to the cost of the green edges, we know that the cost of P has to be less than or equal to the average of the cost of the blue and green edges. You can see this inequality in the third bullet. And as you can see, the blue edges and the green edges make up the entire optimal tour of the graph. So instead of writing the cost of PB plus the cost of PG, we can replace this term with the cost of the optimal tour of the graph. Now we have the cost of P, or the sum of the edges in the lowest cost perfect matching, is less than or equal to 1/2 the sum of the edge weights in the optimal tour of the graph. This is the second important nugget of knowledge to remember, so let's pin it at the bottom again. The last concept we need to cover before explaining the algorithm is an Eulerian circuit. An Eulerian circuit is a traversal of the graph that starts and ends on the same point and goes through all the edges exactly once. Here, let me show you an example so you can see what we're talking about. We can start at 0, and you can see the order of vertices visited in the traversal above. The path we took went through all the edges exactly once and then made it back to our starting point, 0. You can think of this like one of the games you might have seen before, where you have to trace through all the lines on a shape without lifting your pencil or going over a line twice. That's exactly what an Eulerian circuit is. Here, You give it a shot. Let's change up the graph a bit and add an extra edge. See if you can make an Eulerian circuit. Choose any starting point and try to trace all over the edges and make it back to the starting point without going over an edge twice or lifting your finger off the screen. Were you able to get it? Here's an example path that you might have tried, but you see that we get stuck at 4, no remaining edges to exit the point. Here's another try, but now we get stuck at 3, with no more remaining edges to exit the point again. At this point, you might start to get a little suspicious as to if this is even possible, and your hunch would be absolutely correct. It turns out an Eulerian circuit does not exist for this graph. So yes, I did give you a rigged game where you were doomed for failure. But how did I know that? Well, it turns out there's a neat little trick to see if an Eulerian circuit exists for a graph or not without having to trace out a path until you find one that works. And the trick involves looking at the degrees of the nodes. So a node's degree is how many edges come out of it. If all the nodes in the graph have an even degree, then there definitely exists an Eulerian circuit. But if even one node has an odd degree, then there cannot be an Eulerian circuit. So, in this current graph, nodes 3 and 4 have a degree of 3. Because they have an odd degree, an Eulerian circuit is not possible. Before we added the extra edge, they each had a degree of 2, and all the other nodes also had an even degree, so we were able to easily find an Eulerian circuit. You need all even degrees for an Eulerian circuit because you always enter into the node through one edge and exit through another. Each node needs an enter and exit pair of edges, and if you don't have an even number of edges going into each node, then eventually you'll enter a node and not have an unvisited edge to exit the node through. Okay, finally, it's time to go through the Christofides algorithm. We've gone through all the preliminary info, and now it's time to put it all together. Let's say we have a graph G. We first want to create a minimum spanning tree of the graph. We want to do an Eulerian circuit around M in order to get some ordering of vertices that we can use for our approximation tour, but remember, it's not possible because there are odd degree points. You can see all the odd degree nodes with a red outline. For example, node 0 is red because it has a degree of 3, and node 8 is red because it has a degree of 1. So what can we do to make it so that all the vertices have an even degree? Well, we can implement the minimum cost perfect matching on the odd degree nodes. Now we add the edges to the minimum cost perfect matching into our graph. And now we're able to finally perform an Eulerian circuit. Here is the Eulerian circuit for the graph that we have. We're almost done. But before we begin, we have one last set of notations. Let E represent the edges of our Eulerian circuit. The Eulerian circuit goes through all the edges of the graph exactly once. The edges in the graph are just the edges in the minimum spanning tree combined with the edges in the minimum cost perfect matching. The gray edges here are the edges from the minimum spanning tree, and the yellow edges here are from the minimum cost perfect matching. Both these sets of edges combined make up the edges in the graph. Now here is where our early nuggets of knowledge come in handy. Remember, we found earlier that the cost of the minimum spanning tree is less than or equal to the cost of the optimal tour of the graph. We also know that the cost of the minimum cost perfect matching of the odd degreed nodes is less than or equal to 1/2 the cost of the optimal tour of the odd degreed nodes. Well, the odd degreed nodes are just a subset of the full graph. So intuitively, the optimal tour of a subset would be shorter than the optimal tour of the entire graph, because you get to skip over visiting certain nodes. You can see this to the left. The blue edges represent the optimal tour of just the odd degree nodes, while the white edges represent the tours of all the nodes. The optimal tour of the odd degree nodes is shorter because it doesn't have to visit all the nodes. For example, the tour of the odd degree nodes has an edge from 5 to 8, but in the tour for all the nodes, to get from 5 to 8, you have to go from 5 to 6 and then 6 to 8. Going straight from 5 to 8 will be shorter, as the shortest distance between 2 points is a straight line. Because the optimal tour of the odd-degreed nodes is less than or equal to the cost of the optimal tour of the entire graph, we know that the cost of the minimum perfect matching of the odd-degreed nodes is also less than or equal to 1/2 the cost of the optimal tour of the entire graph. So, because the cost of the Eulerian circuit is just the sum of the cost of the minimum spanning tree and the cost of the minimum perfect matching of the odd-degreed vertices, we can rewrite this equation. We can replace the cost of the minimum spanning tree with the cost of the optimal tour of the graph. And we can replace the cost of the minimum perfect matching of the odd-degreed nodes with 1/2 the cost of the optimal tour of the graph. Now we have the cost of the Eulerian circuit is less than or equal to the cost of the optimal tour of the graph plus 1/2 the cost of the optimal tour of the graph. Therefore, the Eulerian circuit is less than or equal to 3/2 or 150% times the cost of the optimal tour of the graph. Now the solution we have right now is the Eulerian circuit of the graph shown to the left, but this circuit visits multiple nodes twice. We're looking for the optimal tour that visits every point once, so we can remove the duplicates from our traversal. The first duplicate node we go to is 0. Instead of going from 4 to 0 and then 0 to 8, we can simply just go 4 to 8. This will only reduce our total cost. Remember, the shortest path between 2 points is a straight line. Similarly, we can do the same thing when 7 appears for the second time. We can remove the edge from 6 to 7 and the edge from 7 to 3 and simply draw an edge from 6 to 3. Now, we have an ordering of nodes such that each node appears only once, and we can make it back to our starting node 0. This, finally, is the Christofides algorithm solution. Our Eulerian circuit of the graph was found to be within 3/2 of the cost of the optimal tour, and we made our path even shorter by not visiting duplicate nodes. So, the Christofides solution must be guaranteed to be within 3/2 of the optimal solution. Just to be thorough, let's see how our Christofides solution for this graph compares with the optimal solution. Here, we see that our Christofides solution ends up with the cost of 33.9, and the optimal tour ends up with the cost of 30.7. Not bad. Just like we proved, our approximation was, in fact, within 3/2 the cost of the optimal solution. This algorithm that we just proved, the Christofides algorithm, once again, is not only the most accurate but quickest heuristic that we can have to solve the traveling salesman problem. Okay, so we went through this whole saga, but what is the point of all this? I mean, sure, we went over trying to solve this little puzzle that was derived from trying to visit all the rides in the shortest amount of time, but besides that, what's so special about this problem? What makes this topic so fascinating is that you can find endless different scenarios where the initial problem turns out to be just the traveling salesman problem in disguise. For example, you could be a bus driver trying to find the shortest bus route that will hit every bus stop in the city. Or maybe an engineer trying to find the optimal placements for components to minimize circuit length in microchip production. Or even a defense scientist helping to program a sequence of attacks for a giant space laser weapon to wipe out thousands of oncoming enemies. I love the traveling salesman problem because of how simple yet perplexing it is simultaneously. The rules are easy enough to understand such that any child could learn how to play the game, yet at the same time there are so many intricate complexities spawning from the problem that have stumped mathematicians and computer scientists for decades. And hopefully, through this little journey, you've been able to appreciate a little bit of those complexities yourself through learning about heuristics, factorial calculation times, and even a smidge of graph theory. This is far from the whole story, and as much as I wanted to, I couldn't fit every amazing detail and side path into this video, or else it would have been way too long. And besides, there isn't time for that anyways, because you finally arrived at Funland Theme Park, and there are so many rides to ride, and only so little time to do it in.